just already seen, luckily, actually for a wonderful keynote. Really looking forward to hearing once again from Professor Muriel Médard. Please be very, very welcome back on stage. Put your hands together. Thank you very much from Optimum. And you'll be speaking to us about building the fastest decentralized internet protocol for Web3. Really looking forward to learning from you, Professor. Welcome back.
Thank you very much. I'm back. I'm still Muriel. And I'm going to talk to you about decentralized internet protocol for Web3. And it's particularly about scaling in a decentralized environment, right? Because we hear a lot about, challenges in one direction or another, but very often they are around really the issue of how do you manage in a decentralized setting. And so there's, a feeling that, well, maybe I need to give up on it, maybe I need to centralize. And what I'll tell you is actually you don't. You don't. And certainly you don't from the point of view of anything that has to do with the data, which is the transmission and the access to data. So next. Thank you. Oh, yeah, amazing. All right, so much better. Yeah, all right. So this is what I've been doing with my career. I've been an academic building decentralized coding. And I think I mentioned before, started doing this when it was considered on the very, very edge of weird. And really, it came out of a very simple belief, which is no network can really scale if it doesn't get to be decentralized at some point. Right, if you think of something like the electric grid, when you see big failures, it's actually really because of excessive centralization somewhere. If you think of the internet, Web 2, same thing. It has to be decentralized. There may be pockets of centralization, but you don't have a single centralized entity that's managing all of Web 2. And Web 3 is built on Web 2 the same way that Web 2 is built on the electric grid. We've been very fortunate to have fantastic backers. We've done our seed round. So what are we looking at? We've heard a lot about TPS, et cetera, et cetera. A lot of the issues around really how much people can do come basically to latency. We saw already different time frames, a few seconds, a fraction of a second, et cetera. But, very high latency, state bloat, right? We heard, for instance, about doing something like DA. That's to try to avoid having to do a direct read because of the state bloat. Scaling challenges, which we see all the time. And basically, this idea that you have to give up, sometimes framed as a trilemma, that you have to give up some decentralization in order to scale. And as we'll see, that's actually not really what's happening at all. So let's start with the first aspect of accessing your data, which is actually propagating it. So suppose I publish a message, I have a source, and I'm using something like gossip. Right? So in blockage applications, this is, block propagation, for instance, in Ethereum, but beyond Ethereum. And basically, this is what we use in order to do attestation, reaching consensus, and also to do state synchronization, right? So you have a network here which is really decentralized. Some other chains may put some structure around it, like for instance Solana and so on. But by and large, you send it out from the source, say the proposer, and then you just let it go and hope for the best. Okay. And some of the gossiping challenges that we have is that current systems are effectively not using the correct math, to put it bluntly. So they have to work on this trade-off between, okay, I want to send out enough that I have forward momentum so that, information is propagating, it's getting to the network, it's maybe getting quickly to my validators. On the other hand, if I send too many shards, I'm going to have a problem with a lot of repeats. And if I have a lot of repeats, then basically I'm going to then be wasting bandwidth, clogging up the bandwidth by telling people stuff they already knew, and that's really inefficient, and it will actually slow down the network, right? I mean, if there was infinite bandwidth, maybe you go, well, I don't care, tell me the same thing over and over again. But that's not what happens. So what we do is we do something different. We actually code, that's to say that we send equations. So for instance here, what happens with duplication is, the messages are themselves variables, right, the numbers. Say that have two messages, x and y. What we're doing right now in duplicating is creating equations which are like x, 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 y, 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 y. And if I asked you, can you give me an equation with x and y? Sure, x is a valid equation, y is a valid equation, but we can do better, right? How about 2x plus 3y, right? Let's go crazy. So basically, that's what we do. We are creating equations, and what we've done is we have gone directly to validators and builders. Why? Not just because, they love the math more than anyone else, we'll look at that a little later, but because they can see, if you will, the immediate benefit. And actually, some of our partners are here. We just met some of them at breakfast and for coffee already this morning. They see the immediate benefit because they get faster transactions. We heard about different upgrades that are going to larger block sizes, larger blob sizes. We can tell, and you can that this is a trend. And you can't just do it by fiat, right? You can't wave a wand and say, from now on, I don't know, gigabit, that's it, that's going to be my blob size. No, that's not how it works. You have to accommodate it, and you have to do it somehow. Okay, so I told you a little bit about these equations. So what do? We have different pieces. This is, shards, basically. And what we're going to make is algebraic mixtures from pieces. And again, rather than just repeating P1 however many times, repeating P2, the coding is recipes for making these. Now, if you use something like a 1950s Reed-Solomon code, we heard of Celestia, that's basically they use what's called a tensor code, which was actually created by my academic grandfather in the 1950s. Basically, what they do is you have to have all of the data available to you to create these equations. What we do is decentralized, so you can take equations by themselves, which do not allow you locally to recover the original data and create new equations that are valid. So network-wise, what's happening is that different nodes, without actually ever recovering possibly the original data, can just recombine and send information. And it turns out that this seemingly insane decentralized approach is provably optimum, hence the name. It actually is optimum, as crazy as it sounds. This is one snapshot. We're doing other things right now, but this is a snapshot we took some time ago. You see on the abscissas along the x-axis time, and then you see delay here, latency, and then you see how many x faster it is. So, basically what you do is you're just speeding things up, right? And speeding things up means that, people can get a benefit, and this benefit is purely from math. Okay, so the nice thing about math is that, it's basically free, elegant, and very environmentally friendly, And that's basically what we do. So we've been very fortunate. We have a few more people who have signed up. And this is basically what we have currently on our private testnet. And so, so if you look at the private testnet, if you look at the TVL there, it represents a little 40% of the staked ETH right now. So, lots of fantastic partners. It's been really, really nice. And as I said, some of them are here. And, what is the underlying element of our network? In the spirit of complete decentralization, it's what we call the flex nodes. So why do we call them flex nodes? Well, they're flexible. They can be large, they can be small. They basically just do what they can when they can to help the network. So what they're doing is they're taking equations that are basically circulating around and creating new equations with that decentralized recombination that we saw before, and sharing those equations with their neighbors who are interested, who are in need of that. So it's very, very lightweight. It's not like running a validator. Say here, you could have, say, a PC, just a laptop. Think about 8 gigabytes of memory and half a CPU pretty much will do the trick. So of course, you could have more, you can have less, but it's, flexible, scalable, permissionless, right? And of course, from the point of view of something like censorship resistant, anybody can go and spin one up. As a matter of fact, we're doing a hackathon right here at Cosmoverse, and the first part of the hackathon is actually people spinning up a flex node. So actually setting up a flex node, and then playing around with it and seeing where you can get the best benefit in the network and so on. So that's what that's basically the backbone. So it's completely decentralized. And again, the funny thing is, you would think surely you can't just let the equations go and, random people sending random combinations. Like, really? This is the best you can do? Yes, this is the best you can do. Okay, this is the best you can do, and there's a very powerful theorem, which was actually not proven by me. It was proven by one of my former students, Brian Hoppler. He was my PhD student at MIT, went then to be a professor at CMU in computer science, and he proved what he called perfect pipelining. And perfect pipelining means that even if you had a network where you had a centralized controller who knew everything for free, not just on time, but ahead of time, and tried to schedule everybody, versus not even bothering to figure out what's going on and just letting this thing go permissionless, just random linear coding, the random linear coding would do at least as well. That's it, So with that, please check us out. We'd love to chat. We're doing more hackathons. The next one's going to be early December in the Bay Area. And then at the start of the year, we're looking to do some hackathons, which are going to be online. So that will give a wider public the opportunity to participate. So thank you very much for your attention.